Okay, the next section will be focused on the description of the membrane structure and their composition. So as you probably already know, there are two main chemical species composing the membrane, plasma membrane of all cells in the living world. A bilayer of phospholipids and proteins, which are positioned across the plasma membrane. Um, so the thickness of this structure is between 5 and 10 nanometers. And the phospholipids are characterized by a polar head and two hydrophobic tails, which face each other, while the polar heads are facing um, the extracellular and intracellular side, respectively. So, as I said, the membrane structure is highly preserved across species. Many bacteria have a second plasma membrane outside of the cell wall made out of peptidoglycan. Also, certain viruses have an envelope made up of a bilayer of phospholipids, including proteins. And you know that the origin of this plasma membrane is the plasma membrane of the host of the virus, such as HIV, but also influenza, such as orthomyxoviridae and paramyxoviridae. And this is a very important point. The membrane structure follows the model of the fluid mosaic. So in 1972, this paper was published showing that proteins are included inside of the plasma membrane, and they can move in the two dimensions. So plasma membranes are composed by phospholipids and proteins. Of course, the phospholipids are much smaller than the proteins, and basically we tend to have around 50 phospholipid units per protein within the plasma membrane. The proteins may have different functions. They may be involved in, cell-to-cell communication, cell-to-cell joint, cell-to-matrix connection, signal transduction, receptors, channels, ion channels across the plasma membrane. But the most important thing is that these proteins can move uh, 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 along the bilayer of phospholipids. So the way this has been proven, that membranes contain proteins as well as lipids, comes from, two main evidence. The first one is that the surface tension of the plasma membrane from real cells did not match the one coming from a model containing only lipids. So it was, and that's how important it is when your mathematical model doesn't work, right? You think that your plasma membrane is only made out of phospholipids, and then you make a mathematical model that describes the surface tension of something made out only of phospholipids, and then the values output by your model don't correspond to the experimental ones, and so you give a post hoc explanation, and this explanation sometimes is true. So in this case, that other than lipids, there are proteins inside. So never throw away the results coming from a model that don't show you what you expect, because what you expect may be wrong. Um, and also these proteins can move, along the plasma membrane. So that is the fluid mosaic model coming from fused mouse and human cells known as hybridomes. So many different types of proteins are found in the plasma membrane. So in this experiment, what the experimenters did was to mark with a fluorophore, which was emitting in a certain wavelength, the proteins on the mouse cell, and then, labeling with another fluorophore the proteins coming from a human cell, generating a hybrid cell between a mouse and a human, and observing what would happen to the two wavelengths of the two labels. At the beginning, they would be, well discrete and separate, and after, more or less an hour, you would have a signal that was a merge of the two wavelengths, and that would be progressive in time, and that was the evidence that convinced us that proteins not only are included within the bilayer of phospholipid, but they can move along the bilayer of phospholipid. So when I say phospholipids, actually it's kind of or when I say lipids, it's a very generic term. There are at least between 500 and 1,000 different lipid species. I don't know half of them. You're not required to know half of them. Of course, we're not living computers, but you should do know the two main components, right? Which are the phospholipids, such as phosphatidylethanolamine, phosphatidylserine, phosphatidylcholine, and sphingomyelin. Um, and very important, the cholesterol. So let's start from the phospholipids. So the phospholipids are characterized by a polar head. The polar head is characterized by a polar group on top of the the polar group is connected to a phosphate. The phosphate is connected to a molecule of glycerol. So as you know, glycerol has three hydroxyl groups, one of which is used, to form a condensation bond with phosphate, and the other two to form a condensation bond with fatty acid chains. And of course, the phospholipids which are based on glycerol are called phosphoglycerides. But then there are other phospholipids which have, more or less the same kind of structure: a hydrophilic head, which is polar, and two tails, which are hydrophobic. But the connector between the two, rather than being glycerol, is sphingosine, and they're known as sphingolipids, without much imagination. Uh, so, you know, depending on what kind of fatty acid chains you have attached to your polar head, you can have different kind of phospholipids. So you do know from your chemistry lectures that when a fatty acid chain, or as a matter of fact, any carbon chain, right, contains sp2 and sp1 other than sp3 um, um, uh, kind of carbons, then sp2 can form double bonds, sp3 can form triple bonds, sorry, sp1 can form triple bonds, but we're not really interested about that. We're mostly interested in sp3 carbons forming, just single bond um, 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 carbon chains, and then sp2 forming double bond carbon chains. And the carbon chains which contain a double bond, known as unsaturated hydrocarbon, bend. They literally have a different angle. And by bending, they put distance between one phospholipid and the other. And as a consequence, the biophysical properties of the plasma membrane will change. The plasma membrane will become more fluid. While if the a plasma membrane contains phospholipids, which are characterized by fatty acids with sp3 hybridized carbons. So with, unsaturated, saturated, fully saturated hydrocarbons. These little tails can pack against each other using hydrophobic bonds, and the viscosity of the plasma membrane will increase. So, of course, you will not have fluid versus viscous. You will have different degrees of viscosity, along a continuous spectrum rather than, two categories, fluid versus viscous. The higher the percentage of unsaturated fatty acids inside of your plasma membrane, the, lower the viscosity, the higher the fluidity. And the viscosity of the plasma membrane is not something that is up for discussion. It is an homeostatic parameter. So it is very important to control the, sorry, I'm having a brain freeze. The percentage, the composition, the relative composition of the plasma membrane in terms of phospholipids containing unsaturated versus saturated fatty acids. Then the other protagonist of this story is cholesterol. So cholesterol is, as you probably already know, a fatty molecule, which is characterized by these 3 aromatic rings and a 5-carbon ring at the end of it. I'm having a brain freeze on what's the name of these of this structure. It's obviously not benzopyrene. It's gonna come to me, but yeah, it doesn't really matter right now. It's just my head wanting to know it right now. Oh my God, what's the name? Yeah, it's gonna come to me. Anyways, the core, the steroid core of the cholesterol, has, this a rigid ring structure, and then a fairly mobile non-polar hydrocarbon tail. And it can have a polar group, right? So the point is that we do find, a certain amount of cholesterol molecules inside of the bilayer of phospholipid. And, actually 20% of the animal cell membrane is made up of cholesterol. So it's not a small fraction. Cholesterol has a huge importance for the survival, so to speak, not so to speak, for the survival of the cell, because it works as a heat sink. Every time there is a peak in temperature, I mean, of course, organisms have different ways of coping with changes in environmental conditions, but it's really amazing. It's really great to see how evolution worked to get things just so fine, in the sense that you can imagine how changing the fluidity, I would like you to try to visualize it in your head, right? How the change in fluidity changes everything in terms of the membrane property, right? It changes the way it's permeable to ions through voltage gated or non-gated ion channels. It changes the enzyme activity, it changes the movement of proteins on the plasma membrane, it changes trafficking, it changes everything. So we want this structure that is, highly dynamic to be somehow stable. And one thing that can change very quickly is temperature. So when there is an increase in temperature, what cholesterol will do is to absorb that heat and keep the fluidity stable. While when there is a decrease in temperature, what cholesterol will do is to release its heat, heat in form of free energy, and once again keep the fluidity constant and avoid that the plasma membrane becomes very viscous. Of course, the range of temperature within which this can work is relatively small, but I mean, don't think about all the regulators like birds or humans or mammals, right? Think about a frog. A frog can live from very cold temperatures to very hot temperatures. And I'm not saying that it's all due to the cholesterol, but the lipid composition, and in particular the cholesterol composition of the plasma membrane in all living thing, especially poikilothermic species, the ones that don't thermoregulate, is absolutely fundamental for their survival. If that was not enough, of course, cholesterol is also the precursor of steroid hormones and bile acids. So another thing you should remember is that the plasma membrane is not symmetrical. So the relative composition of the plasma membrane on the cytosolic versus the extracellular space in terms of what kind of phospholipids it contains is not the same. On the extracellular space, you will have an abundance of phosphatidylcholine, sphingomyelin, glycolipids, while on the internal side, on the cytosolic side, you will have an abundance of phosphatidylserine and phosphatidylethanolamine. Right, so of course, the bilayer of phospholipid can move. The phospholipids can move laterally, very fast, actually, 10 at the power of 7 times per second. They can also flex their tails, and they can rotate, around their longitudinal axis. And finally, they've got a fairly rare movement called flip-flop, which occurs less than once a month. So the fluidity of the plasma membrane depends over their non-covalent bonds, their membrane composition, and temperature, as you can imagine. So I would like you to think about it, especially when you consider the effects of all those plant-derived compounds, which show a clinical effect, show a pharmacological effect, but for some reason do not show any canonical target, if with canonical target you mean a protein against which the protein, the ligand binds with chemical and geometrical complementarity, such as a key in the hole, the famous key in the hole model. One of them is cannabidiol. Cannabidiol still doesn't have a very well clarified mechanism of action. There are some candidate proteins and membrane receptors, but why not the whole plasma membrane? Make cannabidiol be able to change the fluidity of the plasma membrane by just intercalating, such as a molecule of cholesterol. Just go out and think about it. Okay, have I got it? Yes, I think it has been loaded. Right, so the membrane proper proteins can be of different kinds. Here, for example, you see an example of the potassium pump embedded in the plasma membrane, which is getting my so yeah, here you see, I apologize, but my computer is going absolutely crazy with these animations, so I will not show it, but you can see it separately on the PowerPoint presentation, which you will find on Blackboard. But I will not show the animation in the movie because I don't know, the StreamPath just doesn't like it. So this is important because plasma membranes are electrically charged. So we will talk about these in great detail once we will talk about plasma membranes in body fluids and homeostasis. So for now, I just want you to know that the pH inside of the cells is absolutely neutral, is 7.4. And the inside of the cells always have a net negative charge, which means that the outside of the cells always have a net positive charge. Ions are not able to move across the bilayer of phospholipid, but there is, for many of these ions, an electrochemical gradient that pushes them on the two sides of the plasma membrane. It pushes them, it doesn't mean that they go through it. Okay? The electrochemical gradient is a driving force. Whether or not the ion then will move as a consequence of that driving force depends on whether or not there's going to be a channel allowing the ion moving through the bilayer of phospholipid. So the separation of charge generates an electrical potential. This electrical potential is around -70 for neurons. It can range between -30 to -100 millivolts. I wrote -50, but that's a very conservative approach. There are actually stem cells that can rest at -30 millivolts.